Hello, I'm Yuxuan Li from Shanghai Jiao Tong University. I'm glad to share our latest research. Stimulus verification is a universal and effective sampler in multimodal human trajectory prediction. In this paper, we propose a universal sampling process named stimulus verification, which uses a probabilistic model we call stimulus verifier to verify the coherence between the predicted future trajectory and its corresponding stimulus. By highlighting prediction samples with better stimulus coherence, stimulus verification ensures sampled trajectory is plausible from the stimulus's point of view and therefore aids in better multimodal prediction performance. We implement stimulus verification on 5 representative prediction frameworks and conduct exhaustive experiments on 3 widely used benchmarks, and superior results demonstrate the effectiveness of our approach. We will now start presenting our work in detail. The task of multimodal trajectory prediction aims at covering multiple distinct future possibilities with finite predictions. In general, such a prediction pipeline first generates a set or distribution of candidate trajectories with a base prediction model, and then samples from the candidates to get the final outputs. Despite the recent progress in the field of multimodal trajectory prediction, we discovered that most researchers are focused on improving the prediction model M and often neglecting the sampling process, which we believe is also important. Currently, the sampling method in the typical prediction pipeline are either random or Monte Carlo, whereas a handful of works have studied on the sampling strategy and came up with searching for better latent vectors for generative models. Yet such approach cannot be applied to classification-based method, limiting its universality. Furthermore, both types of strategies share a common drawback of ignoring certain key factors that may influence the future, which are commonly referred to as stimuli. Although base frameworks can learn from stimulus information to generate candidate predictions, if such information is missing in the outsampling process, out-of-distribution predictions are still highly probable to be sampled and harm the overall accuracy. On the right side, we show the outputs of stimulus or context-aware models making impossible predictions, proving our point. In this paper, we propose an explicit sampling process called stimulus verification, addressing previously discussed drawbacks. As a fully external process, stimulus verification can be applied to any prediction frameworks, making it universal, and on the other hand, it samples candidates based on their stimulus coherences, maintaining the qualities of the predictions. Stimulus verification is built on a conditionally parameterized probabilistic model called the stimulus verifier, and is optimized by maximum likelihood estimation. Given the stimulus information S of a candidate, we first extract features from S and use the features to parameterize a series of 2D Gaussian mixture distributions, which together with the candidate itself outputs the candidate's likelihood given the stimulus. Such likelihood is then mapped to a coherence score, serving as the basis of sampling. In this paper, we use social and context as stimulus. For context as a stimulus, we represent context information with a semantic map of the scene, and use a sliding window to extract the features. Specifically, for each time step t of the candidate, we crop a fixed size area mt centered at xt from the semantic map, where xt is the position of the candidate at time step t. Such a piece of semantic will be encoded via CNN and parameterize the 2D distribution of delta x, which is the displacement from t to t plus 1. Here we show the learned distributions of context verifier at different time steps of a trajectory. The yellow star in each figure denotes the center of the cropped semantic map, and the red star is the ground truth displacement from t to t plus 1. For social stimulus verifier, we use the neighboring agent's relative coordinates and velocities during the observation steps to represent social stimulus. Here we only use information from the observations as they are unavailable during the prediction horizon. To extract features from a social stimulus, we first consider the information at each time step a complete graph and encode it into representations using a GCN. Afterwards, the representation sequence is then further encoded with an LSTM to get a final feature, which then parameterizes the distribution of the entire candidate trajectory. Here, we also normalize the candidate trajectory so that the trajectory starts from 0 for convergence. We then illustrate the learned distributions of social stimulus verifier, where the social stimulus is shown on the left, and the distributions are shown on the right side figures. Here, the right star denotes the ground truth position at the time step. We now introduce the overall sampling process of stimulus verification. Given a series of candidate trajectories predicted by the base model, we first map the candidate's likelihoods given by the stimulus verifier to coherence scores, and then sample trajectories accordingly. For multiple types of stimulus, the final coherence score is calculated as a weighted sum. When more than one trajectory is required as the final prediction, there is one more step that is essential to the overall output quality. The vanilla stimulus verification process is very likely to sample similar candidates since they have similar scores, but such a property will greatly impair the diversity, leading to poor performances. To tackle this problem, we introduce the idea of non-maximum suppression from the FDE's perspective and ensure that the candidate can be selected only when its FDE with any previously sampled candidates is greater than a certain threshold. We conducted experiments on 3 widely used datasets with 5 base prediction models, and the results all show significant improvements over the baseline. Particularly on the most popular ETH-UCY dataset with SOTA PCCSNet as the base prediction model, nearly 5% improvement is achieved on the ADE and more than 7% is achieved on FDE. We also visualize the coherence scores in their original scenes, where a brighter color indicates better coherence. These results show great consistency with human intuitions, and we can see that trajectories going into obstacles are all given much lower coherence scores. And that's all for our talk. If you wish to dive a little deeper, feel free to check out the codes at the link down below. Thank you.